Hi, and welcome to 7.5H, Vertical Circle. In this lesson, students will be able to create and interpret the free body diagrams associated with an object moving in a vertical circle. So think about roller coasters and loop-de-loops. As a roller coaster navigates a loop, the riders feel what they call in the biz G's. Where do the riders feel the heaviest and where do the riders feel the lightest? What the heck is a G? Well, we know that the acceleration due to gravity is negative 9.8 meters per second squared. So if you were going to accelerate at double this, 19.6, let's say you were accelerating like a centripetal acceleration. You know how we're talking about that? And let's say it's 19.6 meters per second squared. Then you would feel 2 Gs, but I actually drew that in the wrong spot because these people feel lighter. This would make you feel heavier. So instead, let's do half. Maybe we'll do half a G, 4.9 meters per second squared. Let's say these people are accelerating a centripetal acceleration of 4.9 meters per second squared. How many Gs do they feel? Well, you just do 4.9 divided by 9.8, and that's a half of a G. 0.5 times 9.8 is 4.9. So that's how the G's, when they say, "Oh, I'm feeling the G's." All right. If you feel heavier, it's because you're accelerating greater than 9.8 and you have some multiple of a G. And if you're feeling lighter, then it's because you're accelerating less than 9.8. So that's what G's is. Very exciting stuff. All right, so where do they feel the heaviest and where do they feel the lightest? If you've ever been on a roller coaster before, you might have some experience with this. On the bottom, right, here we are at the bottom of the loop. What forces are acting on you? Well, we have gravity, right? That's always going to be the same. Just because you're moving in a circle isn't going to change the gravitational force because that is dependent on your mass. Your mass isn't going to change. And the gravitational field strength, the acceleration due to gravity. And that's not going to change. That's dependent on the mass of the Earth, right? So, what else? What other force is there? If this was the only force, you'd be accelerating downward, but you're not going to accelerate downward. Let's say you're moving with a velocity in this direction, okay? What's going to cause you to start moving in this circle? A centripetal force. There must be some kind of net force that's going to pull you towards the center of the circle. So, what other force besides gravity is there? There is a normal force. All right, so at the bottom, the normal force has to be greater than the weight so that the net force, when you combine these two, is pointing towards the center of the circle. And the net force is the centripetal force, right? Or I should say the centripetal force is the net force that causes you to move in that circle. So this is the first position, so we'll call it normal force 1. Okay. And one more piece before we get into the math. I know you want me to put the equations up because you love the equations, but just as a reminder, we already talked about how the normal force can also be thought of as your apparent weight. So it says, what is the apparent weight? Since the normal force is greater than your force due to gravity, normally if you're at rest, we've been saying, oh, they're just equal to each other. Now look at it. This one is greater than your actual weight. So you feel heavier because the normal force, you're being squeezed into your seat more at that position. And that's going to cause you to move in this circle because you're squeezed into your seat more. And by feeling squeezed into your seat, you feel heavier. You feel like you're pushed down towards the ground more, but you're not being pushed down towards the ground more. You're being pushed down towards your seat. And your mind doesn't think that. It just thinks, wow, I feel really heavy. I feel the G's. Oh, so that's, kind of a nice thing. All right, so if we were going to formally write this in, a nice net force equation, we could say the net force at position 1 is equal to the normal force, which is acting upward minus the weight. Okay? Now the net force is equal to ma. That's Newton's second law. And the acceleration we're talking about is the centripetal acceleration, v squared over r. So the net force is equal to mv squared over r. That's Newton's second law for in terms of a circular motion. This stays the same, and Fg is equal to mg. So if the question is what is the apparent weight, let's solve for the normal force, and now we have an equation that'll tell us the normal force. It's actually telling us what our apparent weight is. Normally we feel mg, but we have this additional factor here. So we're feeling heavier by this much. All right, that's what our apparent weight is. So that's the idea there. All right, let's see what happens at position 2. At this position, you still have your weight, and now what direction is the normal force? You're sitting like this. Whee, I'm going this way, okay? The normal force is sitting, it's going to push you this way, right? It's pushing you towards the center of the circle. Now, if you're looking at, okay, what is the net force in the direction of the centripetal force? Only this is pointing in the direction of the centripetal force. You could say, I mean, a component of Fg is what part of Fg is pointing towards the center of the circle? There's no part of Fg that's pointing towards the center of the circle. If anything, it's like Fg cosine of 90 degrees, and the cosine of 90 degrees is 0 if we were going to find the component. So that's how you would do it formally, but we just won't include it in our net force equation. We'll say the net force, the centripetal force that's causing you to move in a circle, is equal to the normal force in this case. So just to write it in the same orientation that we had last time, now your normal force is equal to your centripetal force, and this is how heavy you would feel. All right, this is how heavy you would feel, and depending on how fast you're going, maybe you feel heavier than you normally would. Maybe this factor is greater than mg, depending on how fast you're going and what the radius is. All right. Now at the top, this is an interesting situation. What do you think the free body diagram is going to look like? Now you're upside down. Well, we know the gravity is always pointing straight down. What direction is the normal force? Remember, you're upside down, so the seat is pushing you this way, right? If I was going to draw my little dude here, all right, all right, the seat is pushing this way. All right, so the normal force is pushing that way. If there even is a normal force, I mean, because if you feel weightless at the top, it's because you're not being squeezed into your seat anymore. So there is a velocity that you could go at where there would be no normal force. But for now, let's say there is a little bit of the normal force. Well, the net force equation looks like this. Remember, the net force is the centripetal force. And in this case, they're both pointing in the same direction. So they're working together to cause the centripetal motion. Now you might say, Mr. Nangle, this is pointing down. Down should be negative, negative, negative. All right. The point here is that we're doing circular motion, and we want to make the net force in the positive direction. So we're making this, the direction of the centripetal force is going to be the positive direction. We'll use that. Okay. So again, the net force is equal to MAC. So this stays the same. Notice mv squared over r, that's the net force, okay, every single time. But it's the sum of the forces that's different. So in this case, since they're working together, you add both pieces together. We have the normal force plus mg together give you this centripetal force. And just like before, if we wanted to find an equation for the normal force, because really we want to know what is our apparent weight. Do we feel heavier or lighter? Let's solve for the normal force like we have been doing by subtracting mg from both sides. And we get this. So now we have our centripetal force minus the weight. So this is going to make us feel lighter than we normally would. If this term was equal to mg, then you'd have mg minus mg, and you would feel your apparent weight would be 0 newtons. You would feel weightless. Your apparent weight would be 0 newtons. So because there's this minus sign here, that means that the normal force at the top is less. than you normally would feel. And then just to be thorough, we want to make sure we go all the way around. This one's going to be very similar to position 2. We have the weight pointing this way, and now the normal force is pointing towards the center of the circle. See if you can pause the video and write your own net force equation for this scenario. It should look like this. There's only the normal force pointing towards the center, so the net force is equal to the centripetal force is equal to the normal force in this case. And then again, just to rearrange it, we just flip it around so we have an equation for the apparent weight. And it's the same as the one that was over here. Here's all 4 together, just so we could compare. At the bottom, remember that the normal force is more than your force due to gravity, because these 2 terms are being added together. And then on the side, it looks like that. It's only the normal forces supplying the centripetal force. And then at the top, the normal force and the weight work together. So you don't need as much of a normal force because you have this weight that's helping with the centripetal force. This is the only point where the weight is fully making you go towards the center of the circle. So the normal force doesn't have to work as hard in order to maintain the same centripetal force. And since the normal force doesn't have to work as hard, that means you're going to feel less heavy than you normally would. And then you could see very clearly now these are the same. All right, so on the bottom, I'm just highlighting that the normal force, the apparent weight, is greatest on the bottom because you're adding those 2 terms together. And you feel the lightest at the top because you have to subtract those 2 terms. So I mean, what's more fun than going on a roller coaster than doing math that is associated with that roller coaster? You thought roller coasters were fun to begin with, but now knowing all this math, I mean, it's even more fun, right? So speaking of fun, let's do a problem with a Hot Wheels car. But instead of a Hot Wheels car, let's use a real car and a real stunt person, and let's drive around a loop like this in real life. All right, so strap in. Now, actually, there's a video of people doing this. It's going to be linked in the extension folder for this lesson. But instead of watching the video, let's do the math because, again, it's more fun. So it says a 75-kilogram stunt person is attempting to complete a full-sized Hot Wheels loop-de-loop. The loop in question is 40 meters tall. Is that telling you the radius or the diameter? It is determined that a speed of 16 meters per second is required to safely complete the loop. What is the centripetal force at all points along the loop? What is the apparent weight at the bottom of the loop? What is the apparent weight at the top of the loop? And what is the maximum amount of G's that the rider feels? If you want, you could pause the video and try this out on your own first. I would start by drawing a free body diagram. So just to make sure we get points for units, let's make sure we write our units on the side, including G equals 9.8 meters per second squared. Don't forget about that one. All right, so we're looking for the centripetal force in part A. Remember, don't overcomplicate it. Fc is equal to mv squared over r, and we have all of those things. So the centripetal force at all points is 960 newtons. Now, depending on where you are in the loop, the centripetal force will consist of just the normal force, or maybe it's a combination of the weight and the normal force together will equal this. But at all points in the loop, the centripetal force, the net force, is equal to 960 newtons. So part B says, what is the apparent weight at the bottom of the loop? Here's our free body diagram again. So the weight is pointing straight down, and we have the normal force pushing up on us when we sit in our seat. The net force is equal to the positive normal force minus the weight. We know that the net force, by definition, is equal to the centripetal force. This stays the same, and we know Fg is equal to mg. We just calculated the centripetal force. it's 960 newtons at all points in the circle. We're looking for our apparent weight, the normal force, and mg is equal to 75 times 9.8. So that gives us a normal force at the bottom of 1,695 newtons. In case you were wondering, your weight was equal to 735 newtons. Normally, the stunt person feels this heavy, but at the bottom of the loop, they're going to have an apparent weight of this much. So they feel heavier at the bottom because they're being squeezed into the seat more. And that squeezing into the seat is going to cause them to move in the circular path. At the top of the loop, you still have weight acting straight down, but now you might have some normal force also helping you out. There is a scenario where we'll do it in the next problem where we want the normal force to be 0. We want to feel exactly weightless at the top. But at this point, to be safe, they said that if you go at 16 meters per second, you'll be safe and you'll still be able to feel some force there. You're still going to be like squeezed into the ramp. You don't want to fall down, right? If the speed is less than the speed that it takes to feel weightless, then you won't stick to the track and you'll fall straight down. So that's not safe. So you want to make sure you exceed that speed to be safe. All right, so let's write our net force equation. What do you think it's going to look like? All right, so the net force is equal to the combination of these two forces. They're working together to create the centripetal force. The net force, by definition, is equal to the centripetal force, and Fg is equal to mg. We calculated the centripetal force before. It's still 960 newtons, but now that 960 is being provided by these two forces working together. This was our weight before, so that the actual gravity stays the same. It's just that your apparent weight, your normal force, is different, and that makes you feel lighter in this case. So we went from 735 newtons. Now we feel much lighter. We feel only 225 newtons. And part D says, what is the maximum amount of G's that the rider feels? So remember that a G is really the acceleration due to gravity, or the gravitational field strength is just your force divided by your mass. How many newtons per kilogram? Now, if we wanted to make like a similar thing, instead of our actual weight, let's find out how many G's we feel by taking our apparent weight and dividing it by our mass. That'll tell us what our acceleration is. So it's asking for the maximum amount of G's, so we'll use the normal force at the bottom, our apparent weight at the bottom, and our mass. We're still 75 kilograms. That doesn't change. So we actually feel 22.6 newtons per kilogram, or 22.6 meters per second squared. But how many G's do you feel is different from this number, right? So we would expect it to be 9.8. It's more, which is what we would expect. When people talk about G's, they're actually dividing those. So 1 G is equal to 9.8. How many G's is this? You take this number and you divide it by 9.8, and then we actually feel more than twice the number of G's. We feel 2.3 G's in that case, right? So if you take 2.3 and multiply it by 9.8, you get this 22.6. So that's how that works when people talk about G's. Pretty cool stuff. So as promised, I have another example here where we're going to feel weightless. So let's use a real world roller coaster, the Green Lantern, Stand Up to Your Fear at Six Flags Great Adventure and Safari. And we're going to find the speed that we would need to travel in order to feel weightless. The question says, the Green Lantern Stand Up to Your Fear coaster at Six Flags Great Adventure features a loop-the-loop that is 121.6 feet tall. Assuming this means the radius is 18.5 meters, how fast must you travel in order to feel weightless at the top? And think about, again, what does that mean if they say you feel weightless? Your apparent weight is weightless. Your apparent weight is 0 newtons. And if your apparent weight is 0 newtons, that means the normal force acting on you is 0. There is no more normal force acting on you because you're not being squeezed into the surface. So you're weightless. So that would occur at the top. And we want to know the velocity that we would need to go into this loop with. So the radius is 18.5 meters. We know that. And then this is the key. You want the normal force to be 0 newtons at the top. And we'll look for the velocity. Same as before, making a free body diagram. We'll put this in for now, but it's going to go away because we actually don't have a normal force here. But just to kind of go back to what we were doing before, we had an equation that looked like this at the top, where the normal force and the weight are acting together. All right. And the net force is the centripetal force. It's equal to ma, but AC, the centripetal acceleration, is equal to v squared over r. So the net force is equal to mv squared over r. And here we go. The normal force, we want that to be equal to 0. So go away, normal force. Only the weight is acting as the centripetal force in this situation right here. At this instant, the weight is the thing that causes you to continue moving in the circle. Okay. Then, because if the weight wasn't here, let's say the Earth disappears and your velocity was pointing this way. Now the Earth disappears. There's no more force due to gravity. Your inertia would make you keep going in that direction. So that's how the weight is acting as the centripetal force at that instant. All right. So then we have this. The masses, you could divide out the masses. They cancel each other out. We're going to get a nice equation for the velocity now. So you cross multiply, you get g times r, and then you take the square root, and you get the velocity that you need in order to feel weightless is equal to the square root of g times r, which is not the square root of 9.8 times 18.5 in this case. So the velocity would need to be 13.5 meters per second. And that's an important speed to know as a designer of roller coasters because you want to go faster than this, just slightly more faster than this, so that you know that the riders aren't going to go backwards or, yeah, that would be not good if that was the case. So make sure that it's at least 13.5 meters per second. That's about it. Thanks for watching and have a great day.